by Farrukh Mukhamedov on Zerotolaw for positive contractions of Banach-Kantorovich spaces. Please go ahead and try yourself.
Okay, good afternoon. Assalamu alaikum to everyone. Do you see my screen?
Yes.
Okay. Yes. So first of all, I would like to thank the organizers to allow me to present my talk. So this talk was done jointly with the late Imam Zanganif. So I dedicate him to this talk. So first of all, I want to talk about this talk about the Zerotolaw for positive contractions on Banach-Kantorovich spaces. But basically this talk will be in twofold. Some kind of extension of the Zerotolaw. First, there is for Banach-Kantorovich spaces, and then also non-commutative versions of this law. Okay, first, let us first recall some notions. Maybe already everybody knows. So basically, I will stick my talk about to the classical L1 spaces and LP spaces, and then its extensions to the other kind of analogous of these spaces. Okay. First of all, I will start with measure space with a sigma additive measure mu, and as usual we consider L1 space, and the operator T is mapping from L1 to L1 is called positive contraction if it is positive, and its norm is less or equal 1. So basically, if we consider Markov operator, which is recurrent in the sense of Harris, then Oray and Jamison proved this kind of convergence for every G, which is orthogonal to the constants. If a non-leaf, the chain is a periodic. So then basically all this related to some kind of extensions in sense of applied in the probability to the convergence of regularity of this what is called Markov processes. And then one of these proofs or analytic proofs of the Jamison array result was obtained by Ornstein and Sacheston in the 1971. And then they formulated the theorem in the following way. So if we consider the positive contraction, then it could be two possibilities. Either this one is equal to 2, or this goes to 0 for every element f from L1. So later on, this result was called strong Zerotolaw. Then, if we consider T is ergodic with this property, and then this one holds, or this goes to 0. And then after Vogel proved uniform Zerotolaw, which was proved in his papers as the following, which can be formulated in the following theorem. So as usual, we take a L1 positive contraction. Then, if for some m is strictly less than 2, then we have this kind of convergence to 0. So this is called uniform Zerotolaw, and then these kind of theorems have this kind of regularity properties of these Markov operators, and then relate to the Markov chains. And then this kind of result tried to extend to some other spaces. And then one of these, and then some Zaharopel tried to also prove this one by reducing this kind of implications. For example, so he proved this kind of implication. So to prove this one, he proved this inequality, and then he proved this kind of implication. Of course, to prove these inequalities, Zaharopel used some kind of theorem related to the dominant contractions. So for example, to prove this implication from 2 to 3, he used this kind of theorem 1,4. So then later on, he tried to extend this result for the LP spaces, but with the condition that P not equal to 1 and P not equal to 2. So P strictly should be positive and P not equal to 2. And then he proved the following result. If this is less than 2, here is a modulus of the positive contraction, then we have this kind of convergence. First, it would be desirable to prove with for all P. Then this result has been proved in the famous paper of Katz-Nilsson and Safriri. They proved in more general setting in terms of peripheral spectrum of this operator type. As a particular case, they can cover this theorem for the even for general QT spaces as well. Then after later on, Wittmann tried to extend this theorem by the proving, so to prove this extending this theorem for 1.5 to the more stronger version. Here is with the same condition, he gets this result with the modulus of the operators. And later on, a lot of people try to extend these results. For example, LP can be replaced with the Banach lattices. And then this 2 is replaced with the square root of 3. This done by the papers of a series of papers of Michelin, Schaeffer, Shep, and Zaharopoulos. All papers are done in some kind of extensions to these spaces, to this kind of theorems for the Rees spaces and other kind of spaces. So at the moment, my talk is related to the extension of this kind of result for the Banach-Kantorovich spaces. Here, by Banach-Kantorovich spaces, we mean L1 spaces. L1 spaces associated with vector valued measures. And then second fold is extend this one to the non-commutative L1 spaces. First of all, development of the integration for the measures with the values of Dedekind complete spaces inspired study of B-complete lattice norm spaces. So this means that we want to study such spaces, functional spaces associated with measures which are taking some kind of Rees complete spaces, okay? And then we want to extend this one to the center, consider the same kind of style for the center valued traces for finite phenomenon algebras. Okay, to be more clear, so I will consider the complete measure space with a finite measure mu. So by L omega we denote the measurable real functions. And then by L naught we denote the equivalence classes, okay? And then here we always consider L naught with all measurable functions. Now I consider E linear space over real numbers, but we take the norm L naught value. But we take L naught valued norm. Okay, so in this case, a linear space with a L naught valued space. Okay, so then this pair is called lattice normed space, and this space is called decomposable. For every x, we have this kind of decomposition where f and g and t join positive elements in L naught. And then for this one, we can find such a x and y with this property. Okay, so this is a standard definition of the BO converging. Oh, wait a moment, sorry. sorry. So suppose now I have a BO convergent. We mean in this term, in this sense. In this sense, here the norm convergence in O convergence, order convergence in L naught. Okay. So lattice norm space, which is called Banach-Kantorovich, which is BO, should be BO complete. Of course, every Banach-Kantorovich space has a module structure. So here is some. I will not skip this part. I don't need. So now, given a complete Boolean algebra, we consider a mapping which maps a Boolean algebra to but the values with the L naught, which is called L naught valued measure. For this L naught valued measure, we define corresponding LP space, which is defined by the following way. So similarly, we define Orlich spaces such a way. So we define this X belongs to the Orlich space when corresponding MX will belong to our L1 space, what we defined before. So these spaces are called Orlich-Kantorovich spaces. So basically, what is interesting is the following one: how we relate these LP spaces associated with these vector valued measures with the usual L1 spaces. So they can be considered as in some sense, a vector bundle of usual LP spaces. So this is not here, this theorem. So vector bundle like this. We can consider these LP spaces as vector bundles of this LP space for each omega. So this is a crucial theorem to establish the Zerotolaw extensions of this L for these kind of spaces. Namely, so before that one, to formulate that result, I call it mapping T positive if it is usual, and then it should be L not bounded mapping if we have this kind of inequality, and the norm is defined by the usual. Of course, here the norm is L not valued norm. So to prove the main result, we need some kind of decomposition of these positive contractions with this property into the fiber bundles of the T with this property when we have this kind of equality. So this means that every positive contraction with this property can be considered as a bundle of measurable positive contraction of each LP omega, delta omega. So using this result, we can prove the Zerotolaw for LP spaces and for Orlich-Kantorovich spaces, which can be formulated as a theorem of 2.3 and 2.4. So this is a Banach-Kantorovich analogous. Here we just taking the 2 multiplied order unit of L naught. Here we are considering order convergence. Okay, so now what we can talk about this non-commutative extension of this Zerotolaw. So first of all, non-commutative extension, we need to consider von Neumann algebra with unit and with faithful normal semi-finite trace tau. And then for this von Neumann algebra, we can associate L1 spaces by the following formula. What kind of? So we need to collect all such X in the spectral decomposition such that this should be convergent. And roughly speaking, so this we need to take all trace class operators. So the norm will be defined as usual in this way. So L1 also can be considered as a pre-dual of our von Neumann algebra. So we call T is positive whenever it takes positive elements on the positive elements. And then it is contraction to have this kind of inequality for all x on L1 self-adjoint elements. So to prove the results, we need the kind of two lemmas. So lemma says that norm of T can be calculated on the positive element, and since these norms for the two positive contractions which are dominated, we have this kind of inequality because this comes from immediately from the norm, since L1 norm is L norm here. So to prove that theorem for in non-commutative setting, we need to use some kind of extension of the Zaharopel theorem in the non-commutative setting by proving theorem 3.1, which says the following. If I have positive contractions with T dominated with S, and then Z and S are commuting, if we have this inequality less than 1, then this is true for all n more than n naught. Of course, when Z is equals to 1, Z equals to identity, we get this kind of inequality, which is the extension of the Zaharopel result in more general setting. So using this one, we want to prove a more general result, which is called Zerotolaw for non-commutative operators. So we always assume our positive contraction satisfies its conjugate has this contractility property. If we have this equality, then it's called unital contraction, or sometimes these kind of operators are called Markov operators. So suppose I have a Z positive unital contraction and Tk be unital positive contractions. All of them are Markov, and all of them are, it is called commuting with Z. So take note, in the non-commutative setting, we don't have some kind of minimum. If you look to this result of the Zaharopel, we do not have this infimum of two positive contractions. We don't have. Therefore, to prove the result in a non-commutative setting, we want to use basically Vogel's result about the Zerotolaw, which can be formulated as just exactly non-commutative version of the Vogel's result, which can be found in the book of Kringer. So if we have these inequalities, see, so in this case, this Z is in some sense plays the role of infimum of the operators. If you have this kind of inequalities, then I have this kind of inequality. So for all n more than 1. But take note here, due to the presence of Z, we don't have a convergence to 0. Okay. This m depends on epsilon. Of course, if Z equals to 1 identity, we recover the usual Zerotolaw. So as a corollary of this theorem, we can get the following result, which is exactly multiparametric extension of the Zerotolaw in non-commutative setting. So now let us consider a very particular case. Now if we consider two operators, commuting operators, if we have this kind of inequality, then we have this kind of convergence. Of course, as an application of this result, we can prove under this condition, my T converges to this projection P. So we have something strong convergence of the positive contractions under this condition. So next one is we want to extend this result for the non-commutative L1 spaces associated with the trace valid trace, with the center valid trace, sorry. So this means that what we have now, before we consider it L1 space with the trace, now in our case, the trace will have a values in L0 with what is called L0 valid trace. For that one, we want to extend that theorem. So for this one, we denote Sn set of measurable operators affiliated with M, and then Z becomes subalgebra of this is center. So center valid trace, we mean this kind of operator from M to Z, which is commuting on these elements, and then positive. So this trace is called faithful if I have this property, and normal. So for this space, now trace valid, center valid trace, it means this. And I suppose I have a fundamental algebra with trace valid trace, center valid trace, and then we can define measure topology, and with respect to this measure, we complete our algebra, Sm set of all measurable elements. In this set, we define, so it is all preparatory result to define L1 space. All these results are needed to define L1 F integrable operators from the measurable operators associated with the fundamental algebra. As soon as we define this L1 space, so for this space, we want to decompose this L1 space into the fibers of L1 spaces with the fundamental algebras associated with the usual traces. So this theorem gives us some kind of a decomposition theorem of L1 spaces into the fibers of small L1 usual L1 spaces. So using that one, and then this theorem, so if I have a positive contraction with this property, then again we can decompose our contraction with this property, and this theorem allows us to prove the main result. This here we essentially use the result of what we proved before. But this theorem 6.4 is some kind of vector valued extension of the non-commutative theorem what we proved before. So this is the last theorem. These are all references. So if you have any questions, please.
So thank you very much.
Thank you.
Thanks a lot for this very interesting talk. Yes, we're open to questions, please. Questions. Well, actually, I have a question.
Yes.
So, you showed this, your results for non-commutative L1 spaces.
Yes.
Would it be possible to prove similar things, say, on maybe on abstract state spaces, which are a bit more general, even?
Yes. Right now we are thinking about this abstract space. Yes.
Okay.
Hello.
Yeah.
Yeah. Yes. Right now we are thinking with my co-author to prove this one for the abstract space. Exactly.
Mm-hmm.
It's already paper in the preparation.
Okay. Thank you.
Further
questions?
Excuse me.
Yes.
What's about hello, Farrukh?
Yes. Yes.
Nice to meet you. If you're working in the positive case, in the positive operator, What about in the general case? It means what about the order bounded case operator or continuous operator, something like this?
For which, in which setting? In the classical L1 space, you mean?
Oui, yes. Yes, in Alois space, yes.
Yes, I told you this result, I told you, wait a moment. So these results, all these results already proved in the Banach lattices and Riesz spaces by the authors, Schaeffer, Scheib, Zaharopel. If you are very, very interested, you can find this Zerotolaw for Riesz spaces. Zaharopel proved it in a paper of Mathematica Portugalia.
No, excuse me. That's my question. If the operator T is positive contraction, if we take now T is not positive, but order bounded, for example.
Okay.
Or continuous, or like this. We can recreate the condition of T. It means
positivity, you mean? Yes, understand. I don't know, because when it proves all of them based on the positivity.
Yes.
Maybe it can be replaced with a modulus one. I don't know. I'm not sure.
If the Alois space is Dedekind complete, for example, I don't know. If it is Dedekind complete, we can decompose T for the positive part and the negative part, and you can. I think that you can do something.
But I'm not sure about it, because the positivity was essential in this proof.
Yes, thank you.
Thank you.
I would suspect that it can't work for non-positive operators, right? For instance, if you take an R2, a rotation